Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the laws of motion applied to panel translation, and we are going to apply the kinetics of rigid body to the plane translatory bodies. Such as the cases which are going to apply here, there are the 6 cases. One of the cases is that motion on inclined plane having a smooth surface. And another case is that motion on inclined plane, the surface is the rough surface case. And third one is the analysis of lift motion. The analysis of lift motion, here it is, we are going to consider under the cases of lift motions, when the lift is moving upwards, what is the acceleration, when the lift is moving downwards, and what is acceleration. These are the 2 conditions we are going to study the analysis of lift motion. And here the 4th one is that analysis of the motion of bodies, 2 bodies connected by a string. This is analysis of motion of the 2 bodies which I already studied. And second case, the 5th case also, analysis of motion of 2 bodies connected by a string. When one body is lying on horizontal surface and another one is hanging. That is, looks like the case 5 is similar to here. It is, there is a surface, one is the body which is hanging, which is lying on the surface, another one is waiting, another one is hanging free. This is the weight W and the weight W1. For those cases, what is the acceleration of these weights? So here, the action of the weight is W1 is acting on that. That is called external net force is acting on the body. Whatever W, is this acting? No. This W is making it is in stable condition. That's why there is no action of force on the string. Now the tension of the string is not considered in this case. The 5th one is that analysis of the motion of the 2 bodies connected by a string, that is also same connected, but it is lying on inclined plane and under is hanging free. Here the surface is the horizontal surface and here it is the inclined plane. But one is lying, another one is free. That's what hanging free in air. So these are the 6 cases which we are going to study under the kinetics of rigid bodies applied for these cases. Let us begin with motion on an inclined plane having a smooth surface. There is a weight, the theta is the inclination theta. Here it is the inclined plane having an angle of that inclined plane with the horizontal is theta, and W is the weight, that is the weight of the body on the surface, and where is acceleration, that is the linear acceleration of the body is A. Now there is a normal, the weight is acting downwards, passing through the center of gravity of the body, and the normal reaction, which is always according to the principle of normal reaction, the normal reaction is normal to the inclined plane or normal to the surface. Here it is. This is the normal reaction which is acting upwards. Now resolve this weight, the angle is made, the normal reaction and the weight, the angle of inclination, it is equal to the angle of inclined plane, that is theta. Now resolve this W into normal to the inclined plane and parallel to the inclined plane. Normal to the inclined plane, that is W cos theta, and parallel to the inclined plane, that is W sin theta. W cos theta and W sin theta. Okay. Now if you resolve the force, which is, we are going to consider which force we are going to consider here. The force which is acting, the body is the motion of the body in this direction downwards, which is coming downwards. So that we are going to consider parallel to the inclined plane. Now the parallel to the inclined plane component is W sin theta. The W sin theta equal to mass times acceleration, that is W by G times A, that is the inertia force. W sin theta equal to W by G times acceleration. Now whatever the acceleration here, W get cancelled, then it becomes G sin theta. The acceleration of the body on the smooth surface is A equal to G times sin theta, where theta is the angle of inclined plane. Now here, why we didn't consider this R and W cos theta? Because the motion of the body is not normal to the surface. It is parallel to the inclined surface. That's why we consider the parallel component of resolution of the weight. Alright. Now that's why here it is W sin theta. W sin theta equal to mass times acceleration, where mass equal to W by G times acceleration. From that, W sin theta equal to W by G times A, and A equal to G times sin theta. This is the acceleration of the motion of the inclined smooth surface when the body is on that surface. Now let us begin with the second here. Further more explanation. Here W sin theta equal to, it is obtained as A equal to G sin theta. It is when the body is down the plane. Suppose if the body is moving up the plane, okay, if the body is moving up, then what will happen here? Then it becomes A equal to minus G sin theta. If A equal to minus G sin theta, that indicates then the corresponding acceleration. Then the acceleration becomes A equal to negative G times sin theta. This A equal to G sin theta is for when the body is moving down. If the body is moving up, A equal to minus G sin theta. Now, the second case we are going to consider, that is motion on an inclined rough surface. When we consider the rough surface, the coefficient of friction is to be considered. Whereas for smooth surface, the coefficient of friction equal to 0. For smooth surface, the coefficient of friction equal to 0. Now, whereas for rough surface, the friction exists here when the body is moving. Now, the body is moving down. When the body is moving down on the plane, then the net force equal to F2 minus F1. That here W sin theta minus F1, that is a mu times R. What about mu times R? That R equal to, according to here, that R equal to normal to, if you resolve the components normal to the inclined plane, R equal to W cos theta. Okay, then substitute in the place of R, W cos theta, substitute there, then F2 minus F1, that F2 equal to W times sin theta minus F1 equal to mu times R. What is that? R equal to W cos theta. Then becomes, the equation becomes W sin theta minus mu times W cos theta. Make it common, W cos theta minus mu times cos theta, sin theta minus mu times cos theta. That is the net force. According to D'Alembert's principle, net force acting on the body and the resultant, the inertia force, both are said to be in equilibrium. Now here the net force, this is net force equal to W times sin theta minus mu cos theta, that equal to mass times acceleration. What is the mass times acceleration? The mass should be converted in terms of the weight, then it becomes W by G times A. Now equate both the equations, then make it common. W here, it will be common, it will be cancelled. Then acceleration equal to sin theta minus mu times cos theta. What is the G? Here G is the gravitational acceleration, theta is the angle of inclined plane, and here the mu is the coefficient of friction. Now the acceleration, this acceleration is the linear acceleration. This acceleration is dependent on the angle of inclined plane and the coefficient of friction. This A is dependent on theta and mu. If the mu increases, okay, it affects the acceleration, and the angle of inclined plane, the angle also changes, also affects the motion of the acceleration of the motion of the body on a smooth surface, on a rough surface. Okay, thus here the consideration is that the case considered, the body is moving down. If the body is moving up, then you have to use the direction, then the formula will be changed here. The expression which obtained here, it will be changed. Now let us solve the problems based on the application of those cases. Here, a body of weight 200 newtons is initially stationary on a 45-degree inclined plane. Here the angle of inclined plane is 45 degree. And here one more thing is that the what distance along the inclined plane must the body slide before it reaches a speed of 2 meters per second. The final velocity was given, that is the final velocity. The coefficient of friction between the plane and the body is mu equal to 0.1. So based on this data, the obtained figure is similar to here. So now it is considered coefficient of friction. What type of case here? Is this the motion on smooth inclined surface? No, it is a motion on inclined rough surface, because the coefficient of friction is given here. Now for that case, the weight is considered how much? 200 newtons is the weight of the body. Weight acts downwards. This angle of theta is 45 degrees. Again, resolve this 200 newtons cos theta and sin theta, that is normal to the inclined plane and parallel to the inclined plane. That's 200 sin 45, 200 times cos 45. Then where is the R is the normal reaction, that R equal to 200 times cos 45. And another one is the net force, that is the net force equal to net force parallel to the plane. Net force parallel to the plane equal to, that is 200 times sin 45 minus mu times R. Now what is the mu equal to? 200 times sin 45 minus mu equal to 0.1, R equal to 200 times cos 45. This is the net force. The net force equal to mass times acceleration. What is the mass times acceleration? Mass m into W by G, that is 200 by 9.81 times acceleration A. Now let us start solving here. The weight of the body 200 newtons, mass of the body, that is W by G, 200 by 9.81, angle of the plane theta 45, initial velocity u equal to 0, final velocity v equal to 2 meter per second, coefficient of friction mu equal to 0.1 and R equal to 200 times cos 45, that is F equal to mu times R, that F1 value is obtained. Now net force, as I told you here, 200 times sin 45 minus 0.1 times 200 cos 45. The value is obtained here, the mass times acceleration. The acceleration here, 200 times sin 45 minus 0.1 cos 45 equal to W by G times A. This equation comes here, W times sin theta minus mu times cos theta equal to W by G times acceleration. Now further simplification, 200 cancel, W has cancelled, then sin theta minus sin 45 minus 0.1 times cos 45 equal to A by 9.81. The acceleration is obtained here, it is 6.242 meter per square second. Now we need to find out the final velocity here, acceleration here. Now carefully if you observe, we got acceleration from there. That acceleration, that is, we need acceleration to substitute in this. That is v square minus u square equal to 2as. That v square minus the v square, v is the value of the v, final velocity is 2 meter per second, and u equal to 0 times 2 times a, acceleration 6.242 times s. Now the s equal to, that is 0.32 meters, that is 32 centimeters. Where it is here, what is required? What is the distance along the inclined plane? The distance required, that distance is 32 centimeters. It moves. Okay. Why we use here the linear, that is kinematic equation. Now the kinetics involves kinematics along with the force. That's why we use force equations, F equal to mass times acceleration, and the force, the equations of motion, that is the equation that is such as v square minus u square equal to 2as. There is another equation, s equal to ut plus of at square. Why we didn't use this equation? Because here the time is not given. That's why what is there without time and relation to initial and final velocity, here the initial velocity is there. Whatever final velocity not there. That's why we used the equation, derived expression, which consists of final velocity, initial velocity and also acceleration plus displacement. That equation we have to use. That's why we use that v square minus u square equal to 2as. Okay. Thus we have to find out the distance travel, that is 32 centimeters. The next equation, now next consideration is that analysis of lift motion. Now the lift which is having, this is the lift is connected here, the pulley is the force, this is the mechanism, of the lift here. Okay, when the lift is moving upwards, the lift is moving downwards. There are two cases. So the weight carried by the lift, that is W, that is mass of the lift, that is W by G, where A is the uniform acceleration of the lift, T is the tension in the cable. Here we are going to consider that this is also called the reaction of the lift. This tension causes the reaction of the lift. Now, the lift can do two things. One is it can be moved upwards or it can move downwards. Now let us begin with the case 1. The lift is moving upwards. When the lift is moving upwards, the acceleration is upwards, then the weight becomes maximum. The resultant is that here, when lift is moving upwards, the tension becomes high. It has to move upwards. That's when net force equal to T minus W. That equal to mass times acceleration. That is W by G times A. T minus T equal to what is the tension in the string? Tension in the cable, that is T equal to W times 1 plus A by G. Okay. Now the second case is that lift is moving downwards. Then the lift is moving downwards. The net resultant force is W minus T. The W minus T equal to mass times acceleration. That is W by G times acceleration. Now here, then again, what is the tension in the cable? That is T equal to W times 1 minus A by G. Here T equal to W times 1 plus A by G when lift is moving upwards. When lift is moving downwards, and T equal to W times 1 minus A by G. These are the things. This is the analysis of lift motion. When lift is moving upwards and the lift is moving downwards. Here it is mentioned here. Now let us begin to solve some of the problems based on those derived expressions. Now a lift carries a weight of 100 newtons and moving with a uniform acceleration of 2.4 meter per square second. Determine the tension in the cables supporting the lift when the lift is moving upwards and the lift is moving downwards. Take G equal to 9.8. Now directly substitute what is the weight equal to 100 newtons here and the acceleration, that is 2.45 meter per square second. Okay, we know that T equal to W times 1 plus A by Z and T equal to W times 1 minus A by G. This T equal to W times 1 plus A by Z when lift is moving upwards, when T equal to W times 1 minus A by Z when lift is moving downwards. Here directly we can substitute W. We need the tension in the cable. For the first case upwards, substitute here value of the W and the G value 9.8, A equal to 2.45 meter per square second. Then the tension in the moving upwards. Similarly, if you substitute, if you plug those values, the values of weight and acceleration in second equation, when lift is moving downwards, you will get the tension in the lift is moving downwards. Lift is tension in the cable. Now, when lift is moving upwards, the tension in the cable is, substitute those values, W equal to 100 newtons, 1 plus A, acceleration 2.45 meters per square second, and G is 9.8. That is 100 times 1.25, that is 125 newtons. The lift is moving downwards, that is T equal to W times 1 minus A by Z. W value, plug those values, plug the values of W, acceleration, and acceleration due to gravity in the equation of the tension, that is T equal to W times 1 minus A by G. You'll get it, the answer, that is T equal to 75 newtons. Lift is moving downwards, tension equals 75 newtons. When lift is moving upwards, tension equal to, that is tension on the cable, that is 125 newtons. Now always understand, the tension is maximum when the cable is maximum when lift is moving upwards. Why? Because lift is moving upward, tension is maximum. The lift weight plus the weight of the body inside the lift, that should be considered. It has to move upwards. When it is coming downwards, okay, the weight of the lift, it is easy when releasing it. That's why it is how many newtons difference is coming. That is 15 newtons difference. Okay. That's why the power consumption is high when the lift is moving upwards, and the power consumption is low when the lift is moving downwards. This is the meaning. From this we can come to conclusion. Now here the point is that in this session we studied, there are two cases, there are three cases we studied here. The thing is that case 1 is the inclined, the acceleration of the body on inclined smooth surface, and second case is acceleration of the body on inclined rough surface, and third case is analysis of lifting machines. In the case of those inclined surfaces we consider only when the body is moving downwards. Okay, for the rough surface and smooth surface. Whereas in the case of lifting analysis, we calculate the tension in the cable of the lift when the lift is moving upwards and the lift is moving downwards. Okay, and also solve the problems by using those derived expressions. The references are used here. It is R.S. Kurmi, Engineering Mechanics by R.S. Kurmi, Irving Shames, Hebler, Beeren Johnston, and R.K. Bansal. These are the references are used and referred and explained in this session. Okay, we can wind up the session for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.